Alright, welcome back everybody. In this video we are going to continue our discussion of section 8.8 of AP Calculus, volumes with cross sections, triangles and semicircles. Excuse me. And we're going to pick up right where we left off. We're going to look at a few more examples from some old AP questions. Here we go, example 3 from the 2019 AP Calculus AB exam, free response question number 5, which makes this a non-calculator question. We've got this region R. Let R be the region enclosed by the graphs of g of x equals blah and h of x equals blah, the y-axis and the vertical line x equals 2 as shown in the figure below. Region R is the base of a solid. For the solid, at each x, the cross-section perpendicular to the x-axis has area a of x equals 1 over x plus 3. Find the volume of the solid. Don't overcomplicate a problem like this. In this problem, they have literally told you this is the area of the cross-section. I know I saw so many of my students, or at least a few of my students, try to really overcomplicate this and use this expression and in conjunction with, h of x and g of x in some way. But this is actually the cross-sectional area. If you remember back when we first started this, when we were finding volumes of the solids, our general approach was take the integral from a to b of the cross-sectional area. So that means that this is our integrand. So we just need to go ahead and put that in as our integrand. And then this is, for r, goes from 0 to 2, so those are going to be our limits of integration. And we can just go ahead and integrate this. This is a natural log of the absolute value of x plus 3, evaluated from 0 to 2. Both of those result in positive values, so we've got a natural log of 5. Minus the natural log of 3. And if you feel like it, you can write that as a single natural logarithm of 5/3. Okay? On to example 4. Example 4, adapted from the 2009 AP Calculus AB exam free response question number 4, non-calculator. Let R be the region in the first quadrant enclosed by the graphs of y equals 2x and y equals x squared, as shown in the figure below. The region R is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis has area. Again, we're told the area of a cross-section. So there's not really any work for us to do here. We're going to find the volume of this solid. It's going to be the integral of the area and now I just need my limits of integration. Since we're talking about perpendicular to the x-axis, it's going to be x-coordinates from 0 to 2. And there's my setup. Again, this is a non-calculator question, so let's find the volume of this solid. That's going to be equal to, alright, the antiderivative of sine of pi over 2x is going to be negative 2 over pi cosine of pi over 2x, evaluated from 0 to 2. And then I can just substitute. That gives me cosine of pi minus cosine of 0. And so this is negative 2 over pi times negative 1 minus 1. And when we simplify all that out, it ends up being 4 over pi. Alright. Part C. Another solid has the same base R. For this solid, the cross-sections perpendicular to the y-axis are semicircles. So we're going perpendicular to the y-axis, which means we want to get these curves, x as a function of y. For the line, that's just going to be x equals 1/2 y. For the parabola, that's going to be x equals the square root of y. And it's the positive branch since it's to the right of the vertex. So those are our curves. in order to find the length of the side, or the length of the slice here, the furthest right point is square root of y, and the furthest left point. So this side here has length square root of y minus 1/2 y. Okay, and if you remember from back when we developed the formulas for area in this lesson, the volume regarding semicircles, this formula for the area is pi over 8 times the side length squared. So this is going to be pi over 8 times the integral of square root of y minus 1/2 y quantity squared with respect to y. And it's going to go from 0 to 4. And now we want to find the volume of this solid. And we're going to go ahead and integrate this by hand, since this is a non-calculator question. So, what do I have to do in order to do this? Well, got to expand this out. So this is going to be equal to pi over 8 times the integral from 0 to 4 of y minus 2 times the product of these. So let's see, 1/2 y to the 3/2. So that's going to end up just being minus y to the 3/2. And then plus 1/4 y squared. And now I'm going to go ahead and take my antiderivative. It's going to be y squared over 2 minus 2/5 y to the 5/2, and then plus 1/12 y to the 3rd, which we're going to evaluate from 0 to 4. So we've got pi over 8 times 16 over 2, which is 8, minus 2/5 y to the 5/2. So y to the 5/2, that's going to be 32. So that's going to be minus 64 over 5, plus 1/12 times y cubed. 4 cubed is 64. 64 over 12, that's going to be 16 over 3. And this is a totally acceptable answer here, by the way. And that's minus 0 plus 0 when we put the lower limit of integration in. This is a totally acceptable answer here. I'm going to clean it up and turn it into a single fraction. Let's make all of these 15ths. So we've got 120 15ths minus 3 times that. That's 192 15ths. And 5 times that. That's 80 over 15. And that ends up being 8 over 15. So we've got pi over 8 times 8 over 15. And so the volume of this solid should be pi over 15. All right, there you go. That takes us to the end of this lesson. There's some practice problems for you to do. You want to make sure you go ahead and do those, and we'll see you next time. Section 8-9, we're going to get into volumes of solids of revolution next. All right, have a great rest of your day, everybody. See you in the future. Bye-bye.